Hi guys, welcome to our channel, and for today's video we will discuss about the gas and vapor power cycle. So let's start. Problem number 2. The operational cycle of a steam power plant is depicted in, so if the turbine isentropic efficiency is 87% and the pump's isentropic efficiency is 90%, determine the thermal efficiency of the cycle. So we have a given of isentropic efficiency, which is 87%, and the isentropic efficiency of the pump is 90%. So we have, or we are looking for the thermal efficiency of the cycle. So let's start in solving this problem. So solution. So here, as we can see, a steam power cycle with specified turbine and pump efficiencies is considered. So the thermal efficiency and the net power output are to be determined. So steady operating conditions exist, yes, as we can observe. Kinetic and potential energy changes are negligible. So the schematic of the power plant and the TS diagram of the cycle are shown. So the temperatures and pressures of steam at various points are also indicated on the figure. So we note that the power plant involves steady flow components and operates on the Rankine cycle, but the imperfection at various components are accounted for. So let's solve for thermal efficiency of a cycle. So let's start in solving the work of pump. So here, the formula that we will be using is work, or WS, of pump in over NP, or yes, equals to V1 to the quantity of P sub 2 minus P sub 1 over NP. So let us substitute the values. For work sub S of pump in, we have 0.001009 cubic meter per kilogram. For V1, we have 16,000 minus 9 kilopascal. Okay, over our NP, which is 0.90 or 90%. So as we can see, some of the givens are in kilopascal. Thus, we should convert it into kilojoules by multiplying 1 kilojoules over 1 kilopascal per I times cubic meter. So let's solve for the value of our work of pump. We have 17.93 kilojoules per kilogram. So let's proceed. We will solving the value of turbine work output. So we will be solving it by the formula, which is work of turb out equals NTH WS turb out. So NP, so quantity of H sub 5 minus H sub 6S, so H for enthalpy. So we will change the, or we will substitute the NT for 0.89 and H5 for 3,583.1 minus 2,115.3 kilojoules per kilogram. So by solving it, we will now have the value of our turbine, which is 1,306.34 kilojoules per kilogram. So let's proceed in solving the boiler heat input. So we simply put the formula, which is Q in equals H4 minus H sub 3. So let's substitute H sub 4. So we have the value of H sub 4, which is 3647.6 minus 160.1 kilojoules per kilogram. So let's subtract it. So we have 3487.5 kilojoules per kilogram. So let's proceed in solving for work net or input network. So we will be using the work of turbine out minus work of pump in. So let's substitute the values. For work of turbine, we have 1306.34 minus 160.1 kilojoules per kilogram. So we have work net or input network, which is 1146.24 kilojoules per kilogram. So finally, we will now have to solve the thermal efficiency, and this part is the one we were looking for. So the thermal efficiency or NT is equals to work net over Q in. So as you can see, we already have the value of our work net, which is 1146.24 kilojoules per kilogram, and also we have the value of our Q in, which is 3487.5 kilojoules per kilogram. So we just simply divide it in our calculator, so we can have now the value of our thermal efficiency, which is 0.33 or 33%. So this will be the end of our tutorial. Thank you for listening, and God bless everyone. Bye bye.